Hello everyone, welcome to Big Data Thoughts. Today we are going to discuss about stream processing. So this is the first video which talks about very basics of what stream processing is, what are the fundamentals, benefits, challenges, what to keep in mind when we are designing a stream processing system. So let's get started. First of all, let's start by understanding what is streaming. So, what is stream processing really? Stream processing means there is a continuous influx of information. Just think about it simplistically as a system that is capable of ingesting data continuously to compute a result. So, it's an act of continuously incorporating new data to compute some result. Now, when we talk about stream processing, the input data is unbounded, and that's the whole point of having streaming data or data which is coming in near real time, right? Because there is no specific beginning or end, it is completely unbounded. It's like a stream of data coming in. It's series of events that are arriving at the stream processing system. Now, when we look at stream processing, we should not think that the data that we are getting and we are trying to process is only a stream, because most of the cases what you will see is it's a combination of stream and batch processing. So there are architectures that were proposed some like long back, like lambda architecture, which actually spoke about having both of these stream and batch put together in that architecture, because it makes complete sense to have data which is coming in batch, or the data which is already residing in your data platform from like previous years, and now you are getting data which is coming in as a stream, and you want to capture that data, process it, and ultimately join it with the previous data. So it's always a combination of stream and batch processing, because your streaming applications would need to join input data against a data set which is already getting written periodically by a batch job. An output of the streaming job is often files or tables that are queried in batch jobs. So it's, if you look at real world use cases or any data platform which incorporates a streaming architecture, you would also see certain batch processes already there which are ingesting data, and then you're combining the streamed data into that batch. The business logic that any application needs to work on is consistently working on both streaming and batch. Particularly if we look at lambda architecture, and maybe I'll talk about lambda in a separate video altogether, you would have both the flows, the batch, the stream, and your output would actually utilize both as and when needed based on your use case. But think of streaming as a continuous influx and batch as a periodic influx, and the combination of both can give you actually a lot of useful data for multiple use cases. Now, what are some of the use cases? There can be multiple scenarios where you can use stream processing, but some of the very prominent ones, or few examples if I have to explain, is alerts and notification. Let's say you have let's take an example. You have a number of oil drilling, it's an oil drilling scenario. Let's say you have a number of machines that are involved in this whole process, and those have sensors. Now, this is typically a IoT use case also, but think of it that you want to real time have alerts if those anything goes wrong in those machines, or if there is a threshold defined on them and it gets breached, you want to get immediately notified. So I would say it's a combination of an IoT and streaming use case where you are influxing this whole sensors data in real time for you to capture any deviations, any problems that are occurring, and send an alert or notification to the concerned team. That can be one of the use cases. The other use cases can be incremental ETL. We have known about ETLs since a long time, or ELT in the big data world, where it was scenarios where we were doing it in batch, ingesting data, loading it, transforming it, right? But there may be scenarios where you don't want to wait for the things to happen in a batch fashion. You want to capture whatever data comes in. Let's think about event driven system. Whenever there is data, an event gets generated and that is getting captured. This is also a streaming use case where you are capturing incremental data coming in as and when it comes at the same time and doing the ETL. Another use case would be real time reporting or real time decision making. Some of the scenarios where you do not want to wait for making any decision, like the example I gave about alerts and notifications, where you are trying to read data from sensors in all the machineries that are getting used to know if something goes wrong. Now, that can also be a case of real time reporting and decision making, because if one of the machines, let's say there is a threshold of temperature, it crosses that temperature, there is a risk of that machine uh, breaking down. So in that case, you want to do a real time decision making and say, okay, I want to turn off this one and use some other machine, or I want to send someone to look at it. So any scenario where you want to do alerts, notifications, reporting, or decision making in real time is actually suitable for a stream processing use case. You are sending smaller incremental data and processing it as and when the data comes. Now, what are the benefits? Two primary benefits that I would talk about. Of course, one is low latency. Wherever your application needs to respond very, very quickly and you cannot wait. Those are the ones which are real candidates for stream processing. And it is efficient. Efficient, you can look at efficiency in different dimensions, like you can do more real time reporting, you can take informed decisions very very quickly, you can act upon the data quickly. So in those terms it is efficient, it has lower latency. But everything comes with pros and cons. So if stream processing is such a lucrative thing, why don't we always go for stream processing, right? Why? Because there are certain challenges that are associated with stream processing. What are those challenges? So it may look like to you for a second that okay, benefits there are only two and so many challenges, but it's not like that. These challenges somewhat are remediated or elevated by using stream processing technologies like Spark streaming, or earlier we were using Apache Storm, then there was Kafka and all of that, because those frameworks or those technologies take care of many of the things that you don't have to personally go and code for or do it. But still, it is good to know what are the challenges that are there with stream processing. So, one of the challenges can be processing out of order data based on application timestamps. It is possible that the system is generating data through you, let's say through an event hub. Now that data can become in can be out of order. So if event 1 was generated, then event 2 was generated, but while fetching the event you got event 2 first, so it is out of order. How do you handle that? So there are ways to handle it. You have timestamps, but yes, this is something which needs to be considered. You have to maintain large amount of state. There is state management that needs to be done. We have to support high data throughput because there is huge amount of data coming in at a very short span of time. So there is a high throughput that needs to be handled by our system. Processing of each and every event exactly once despite machine failures. Now most of this, as I said, would be taken care by the technology you are using. But this is what is there. And if you look at the progression of how these technologies were developed, initially when Apache Storm came in or there were other technologies, there were still needs to manually go for somebody who's using those to actually go and code for these scenarios of maintaining state, of maintaining order, etc. But with the advancement in the stream technologies, now you would not face so many challenges. The technologies would themselves provide you declarative APIs to do these kind of things. But coming back to the challenges, so we need to make sure that every event is only processed once and not twice, even if there are failures. We have to handle load imbalances and stragglers. Then one of the challenges could be, how do you actually respond to events which are coming in so frequently in near real time or real time? And how do you join it with the external data, because this influx is pretty quick? How do you read quick, process quick, and send it for consumption? It's not just reading, it's reading, processing, and sending for consumption. Then joining it with external systems, determining how to update output syncs every time a new event comes. How do you make that updation to output sync? How do you write data transactionally to output systems? How do you update your application's business logic at runtime if there is a need? So these are some of the things that you need to think through while designing a stream based processing application or stream any kind of streaming use case that you're implementing, you need to think through all of these scenarios and see how are you handling it. Now let us look at few design considerations. We looked at water stream processing, the benefits, the challenges, use cases, but it is important, like I said, the challenges will give you a quick, like it gave you a quick glance of what needs to be kept in mind. But let's specifically talk about three or four things which we need to think when we are designing streaming systems. First of all, there is a concept of record at a time versus declarative APIs. Let's understand what this is. Now, what is record at a time? As the name suggests, every event is passed to an application and the application is allowed to react to it using a custom code. What it means is there is a source system which is continuously sending events to your application. Now, you have written a custom code to read the data and do something upon it. So record at a time means you're reading each event, you're treating it as a separate entity. You're reading it and executing your custom code. Programming these systems correctly is a bit challenging because at the lower level, and Apache Storm, when it came in, it was actually based on a record at a time kind of a concept where you had very low level APIs where you could fetch the event and work on it. But this required a big, deep expertise to develop and maintain this low level APIs. So it's just like that, right? As and when the technology progressed, you started having functional APIs, declarative APIs, which could do most of the thing for you, and you had to just write the logic, the business logic. But to start with, when Apache Storm came in, or initially when streaming began, it was recorded at a time, which had low level APIs. If you have low level APIs, you have to know much more than, have a deep expertise basically to write the code. Later on, as and when we progress, right, now applications have to just specify what they want to compute, but they don't have to worry about how to compute. So many of the challenges we spoke about in the previous slides would be taken care of by the system itself. For example, Spark streaming. It's pretty advanced than how we used to use Apache Storm. So you just don't have to bother about how to compute. You focus on what to compute, your business logic. And you just application will specify what to compute and to each new event and how to recover from failure. So recovery of failure, how to respond to events is not something that you need to bother. You just need to bother about what business logic you want to implement. Let's understand what is event time versus processing time, because you will keep hearing this term when you're using stream applications. So it's important to know what's the difference between both of them. What is event time? As the name says, event time is the idea of processing the data based on timestamps inserted into each record. So whenever that record was generated, there was a timestamp that would have been generated, which tells you which event was generated first, which was generated later. So if there is an out of order problem, you would still know with the timestamp the sequence of the events. So event time is nothing but the actual time when the event got generated. It is not the time when the record is received by the streaming application. That's processing time. So that's the distinction. When the record was generated, that time is known as event time. When the record was received at the streaming application, that's the time which is known as processing time. So event time is very useful when you want to find out the order in which the events are getting generated. Processing time is, as I said, when the record was received, it is that time. So if your application is collecting data from remote sources, there is a possibility due to network lags, because just previously we spoke about IoT use case, right, for streaming. In those scenarios, the devices or the source is at a remote location. There can be network lags, there can be out of order scenarios. So it is very, very crucial to look at the event time. Otherwise, you may miss certain patterns, right? So while designing a system, keep in mind about event time versus the processing time. Now, continuous versus micro batch execution. Let's just quickly talk about this too. What is continuous processing? Now, we know continuous processing based systems, streaming is itself a continuous influx of data. But in streaming also, you can have two varieties or flavors. One is where you are constantly getting data influx. Each node in the system is continuously listening to messages from other nodes and then outputting that to its child nodes or making updates, executing the logic. This continuous processing has an advantage of offering lowest possible latency because you are generating data from source as and when the source gets the data. So it's a continuous flow. It has very low, it has a very good advantage in terms of latency. However, it will have lower maximum throughputs because there is a significant amount of overhead per record. When we are sending each record as and when it comes, my batch of the data or my size of the data is pretty small. The throughput can be low, but you will have low latency. Now coming to the next flavor, there can be another type of stream processing which is micro batch system. What it means? The name has batch. So what it signifies is it's a micro batch. Since we are talking about real time stream processing, what you are doing, you are not sending the event as and when you receive it, but you are waiting for some time to accumulate a small batch of input data and then you are processing each of these batches in parallel by using a distributed collection of tasks. Now, this is very similar to the execution of batch job in Spark. Spark also does the same, right? Now, micro batch system can often achieve very high throughput per node, but they will have certain cons like the latency would be a little bit longer. The reason being you are waiting for accumulation of a batch, which is a very micro batch, and then sending the data. But both of these are a good way of handling stream processing. It depends on what kind of use case you have. If it really needs some real time decisioning and you can't wait, then you go for continuous processing based systems. Else you can utilize, if you're doing an incremental ETL and you don't have really a scenario where you have to respond absolute immediately, you can think about a micro batch system. It will have low overhead per record because your record size has now increased a bit. So that's how you distinguish between continuous and a micro batch. So these were some of the nuances we spoke about. Now another thing, important thing, like I said, both of these are important, continuous and micro batch, but how do you know which one to use when, right? That would be the next question. So there are two things that we need to keep in mind to decide what to use. One is the latency that we need. Second is the total cost of ownership or total cost of operation. Now, in a micro batch system, we can deliver latencies from 100 millisecond to a second, depending on what my application is. It will generally require fewer nodes to achieve the same throughput and it will have a lower operational cost. So, you will have a lower maintenance cost also, lower maintenance cost due to less frequent node failures. Okay. If you need much lower latencies, then you should consider a continuous processing system or you should use a micro batch system in conjunction with a fast serving layer. So if your requirement is absolutely real time, then you go for continuous. If your requirement is or you're okay to have a micro batch is better in terms of throughput, in terms of the cost of total cost of operation. So this decision should be made based on the use case that you're trying to serve. Okay. Now this was all about what is stream processing, benefits, challenges, use cases, some of the design considerations. I hope this gave you a good preview into what stream processing is. And please like, share and subscribe to the channel and keep watching for many more interesting videos. Thank you.